Okay, thanks everyone for being here. It's my great honor and pleasure to be here. Like Pratik said, this is our annual event in Singapore, hosted at NUS. In the last several years, we have done the workshop focusing on the intersection of AI and security. And given the amount of interest in blockchain and so on, so this year we focus on blockchain. And thanks everyone for being here. And as Pratik mentioned, right, so I'm a professor at UC Berkeley in computer science. I've been a professor there for more than 10 years. And my research has been in computer security and privacy, and also my group, we have done a lot of work in AI and deep learning. And also more recently, we have been doing a lot of work in the area of blockchain. And besides just doing research and teaching classes in blockchain, recently, so me and some of my students and postdocs and other collaborators, we have started a company called Oasis Labs, which is what I will be talking about today, focusing on building privacy-first cloud computing platform on blockchain. Okay, yeah, thanks everyone. So today I'll talk about what some of the new technologies that we are building towards building a privacy-first cloud computing platform on blockchain. So as we all know, data is the new oil. Data help us to extract insights and help us make better decisions. However, a lot of data is also very sensitive. And handling the sensitive data has many challenges. So first, we continue to see really huge data breaches happening at companies. Oftentimes, we see that attackers steal sensitive information about hundreds of millions of users in one go. And also at the same time, a lot of the valuable data is being siloed. For example, it's very difficult for medical researchers and pharmaceutical companies to gain access to medical data to do the medical research that they need to help find better cures for diseases, and all because of the challenge in dealing with the sensitive data. And also at the same time, we see that users are losing control of their data, as evidenced by the recent Cambridge Analytica incident and many other news headlines that you probably have seen recently. Towards addressing many of these problems, at Oasis Labs, we are building a new technology, building a new computing paradigm, where we build privacy-first cloud computing platform on blockchain with a unique set of properties and capabilities. So first, with a strong security and privacy protection, and second, providing high performance, in particular to enable real-world class-scale applications wide-ranging from games to machine learning. And our technology will also support, with built-in support for privacy-preserving data analytics and machine learning. And we hope to achieve all this with decentralized trust without relying on any central party. So first, let me give you a motivating example, a concrete example illustrating what kind of problems this type of technology can help address. And let's look at the domain of fraud detection. So when banks give out loans or providing other types of financial services, they need to do fraud detection to detect fraud. And this is how fraud detection typically works today, is that each bank usually utilizes its own data to try to build up, for example, machine learning models and other types of mechanisms to detect fraud. However, as we all know, with machine learning, typically, the more data you have and the more diverse type of data you have, then the machine learning, the trained machine learning model can have higher efficacy. And hence, it would be really nice if instead of each bank builds its own fraud detection, it would be very nice for the different banks to pull data together to then help train a better machine learning model. However, this is not done today due to a number of challenges, including that data is very sensitive, and hence there's a lot of security and privacy concerns for sharing the data. And also there can be, for example, misaligned incentives and so on. So with the technology that we develop at Oasis, we can enable a different approach to this issue. So instead of having each bank to build a fraud detector using just its own data, we can, on top of the Oasis blockchain platform, we can build a fraud detection smart contract, whereas the smart contract can pull data from the different banks, and then utilizing the data from different sources to build one fraud detection model. And in this way, again, by pulling data from different data sources, the hope is that the trained machine learning model can have higher efficacy and hence can provide better results for the banks. However, in order to address this, in order to enable this type of application, we need to address a number of challenges. So first, again, the financial data here used to train machine models is very sensitive, and the computation on the blockchain hence and can happen on different types of workers. And hence, it's very important for us to ensure that the computation process does not leak sensitive information, even when the compute workers may not be trusted. And secondly, the computation results, for example, the trained fraud detection model itself may be leaking sensitive information because the computation results is computed from sensitive input to start with. And hence, we need to protect the computation results from leaking sensitive information. And another challenge is, again, here we are dealing with a lot of data and a lot of compute. And as many of you may know today, that today's blockchain platforms have very poor, most of them have very poor performance and have very high costs. And hence, in order to support this type of applications, we need to build new blockchain architectures to enable much greater scalability, in particular for this type of much more complex smart contracts. So at Oasis, we are building new technologies to address these problems. In particular, at Oasis, we are building privacy-first smart contracts at scale. One of the key primitives provided by the Oasis blockchain platform is what we call privacy-preserving smart contracts. So smart contract is just a piece of code that is automatically run on the blockchain platform. On the Oasis blockchain platform, we enable privacy-preserving smart contracts with a unique set of properties and capabilities. So first, we provide automatic enforcement of codified privacy requirements. So privacy requirements for the smart contract, in this case, is encoded as code inside the smart contract, and the Oasis blockchain platform will enable the automatic enforcement of these codified privacy requirements. And also, we hope that we can achieve this without relying on any central party. And the Oasis blockchain platform is designed to scale to real-world applications, including data analytics and machine learning. And another important motivation for the technology that we are building is that we want to develop technologies that can make it much easier for developers to build privacy-first applications without needing to be a security or privacy expert. So a lot of the security and privacy problems that we see today is largely due to the fact that we do not have sufficient security and privacy technologies that can make it easy for developers to build privacy-preserving applications. We hope that the technologies that we are developing at Oasis can help change that and can help develop the techniques and tools that are needed to help developers to build privacy-preserving applications without needing to be a security or privacy expert. So now let's dive a little deeper in terms of the component technologies that we develop in the Oasis blockchain platform to enable this privacy-preserving smart contracts at scale. So when you look at the Oasis the blockchain platform, so there are two layers. So one is the platform layer, and above the platform is the application layer. That's where the smart contract sits. And so first, in the platform layer, we design and build confidentiality-preserving smart contract execution technology to protect the computation process from leaking sensitive information. And then at the application layer, we build technologies for privacy-preserving data analytics and machine learning as frameworks to support these privacy-preserving smart contracts, and with the goal to protect the computation outputs from leaking sensitive information. When we combine the confidentiality-preserving smart contract execution at the platform layer and the privacy-preserving data analytics and machine learning at the application layer, we enable privacy-preserving smart contracts. And to enable scalability at the platform layer, we design and build new blockchain architectures to enable scalable smart contract execution, in particular for complex smart contracts. So now let me talk a little bit in more detail for each one of these component technologies. So first, let me talk about the component technology for confidentiality-preserving smart contract execution. So again, as I mentioned, smart contract is essentially a piece of code that automatically runs on top of the blockchain platform. So typically, users can send requests, can send an input to the smart contract as a request, and then the smart contract then processes requests to transition from the old state to the new state. So on most of today's blockchain platforms, the data and state of the smart contracts are kept in public, and hence most of today's blockchain platform cannot provide protection for sensitive data and compute. And as we just saw, for many applications, including financial services and healthcare and also IoT areas, a lot of the data is really sensitive, and hence we really need to develop smart contract execution that actually can help protect the confidentiality during the smart contract execution. So in Oasis, we build a technology for confidentiality-preserving smart contract execution, where the data and also the smart contract states are all encrypted. So the users in this case, they send requests with encrypted inputs to the smart contract. The smart contract then performs the execution, essentially in a way to execute over encrypted data to transition from the old state to the new state, while the smart contract states are being stored in encrypted form. And one important point to note is that even though the execution is happening essentially on encrypted data, so to the outside, for example, to the other workers and to the outside world, they cannot see what actually has been executed. But however, at the same time, we want to provide a proof of correctness to ensure that the smart contract execution is correct. So at Oasis, we leverage and employ a number of different types of secure computation techniques to achieve this confidentiality-preserving smart contract execution. So the goal of secure computation is to protect the computation process from leaking sensitive information. And in general, there are two different approaches for secure computation. The first one is to use a secure hardware-based approach. And the advantage of using secure hardware is that the performance is really good. Oftentimes it's close to native performance. And also it can support for general purpose computation. Another type of approach for secure computation is based on cryptographic-based techniques, such as secure multi-party computation. The challenge for this type of approach is that the performance overhead can be very high, oftentimes orders of magnitude higher than a native computation, and hence can only be used for supporting limited use cases. In the Oasis blockchain platform, we plan to use a combination of these different types of techniques to enable confidentiality-preserving smart contract execution. So first, here, let me talk more about the secure hardware-based approach. So secure hardware is essentially utilizes hardware-based capabilities to provide a fully isolated execution environment, oftentimes called a trusted execution environment T, or a secure enclave. So when we run a smart contract inside the secure enclave, the outside, for example, operating systems and other applications will not be able to access what's running inside, and also will not be able to modify what's running inside. And hence, the secure hardware helps provide the confidentiality and integrity protection. And also, secure hardware, secure enclave provides hardware-based capabilities called remote attestation, where it allows a remote verifier to remotely verify what has been running inside the secure enclave and also its initial state, and hence to allow the remote verifier to verify the correctness of the execution. In our earlier research, we were the first to develop a system and also writing a paper to demonstrate how we can use secure hardware to help build a confidentiality-preserving smart contract execution on blockchain. And we provide security proof for the design, for the security of the design. So secure enclave, as we just saw, can help to enable confidentiality preserving smart contract execution. In addition, secure enclave is an important building block in particular, can really serve as a strong cornerstone security primitive for building secure systems in general due to its strong security capabilities. And for example, secure enclave can help authenticate itself, the device, can help authenticate the software, and provide strong guarantee for integrity and confidentiality of the execution. And secure enclave can be used for building as a platform for building new security applications that couldn't be built otherwise for the same practical performance. All the hardware manufacturers have recognized the importance of building secure hardware. And over the years, they all have built different visions and different types of solutions for secure hardware. However, there are still many challenges for building secure hardware. For example, how secure can it be? And what threat models? And what would you entrust with the secure hardware? Your Bitcoin keys, your financial data, or your health data? And the ultimate question is that, can we create a truly trustworthy secure enclave that can be that can serve as a cornerstone security primitive that can be widely deployed to enable secure systems to be built on top? And if we can achieve this, we can really usher the whole community into a new secure computation era. So what's the path to building a truly trustworthy secure enclave? One, we need to have an open source design. An open source design of secure enclave can help provide the transparency that's needed for the whole community to come together to analyze the security and correctness of the secure enclave, and also to enable the high assurance that's needed for a secure enclave. And also, open source design help build a whole community. Ideally, we also want to enable formal verification of the secure enclave design. And also, it's important that we can ensure secure supply chain management for the hardware manufacturing process. Towards addressing these challenges, in collaboration between UC Berkeley and MIT, we have been working on a research project called Keystone for building an open source secure enclave. Keystone, as a first step, it's being built on top of a RISC-V architecture for building the open source secure enclave. And RISC-V architecture is a RISC architecture. It's an open source RISC architecture that has been developed at UC Berkeley and that has seen broad industry adoption. For example, the RISC-V Foundation has more than 100 members. And also recently we hosted the first workshop on building open source secure enclaves, and with the goal to bring together experts and researchers from different fields, including architecture, systems, security, and so on, and to come together to build open source secure and performant enclaves. And it was great to see that the leading experts and researchers from industry and academia, including Google, Facebook, Microsoft, Intel, ARM, and many other places, all came to the workshop and together building a community for towards building an open source secure enclave. So that's the first component technology on confidentiality preserving smart contract execution. So now let me move on to the second part, the second component technology on privacy preserving data analytics and machine learning. So first, let me motivating the problem with some concrete examples of our recent work, showing why we need to be careful about protecting privacy for even as we train machine learning models, and in particular why we need to protect the computation results from leaking sensitive information about the inputs. So here in one of our recent work, in collaboration with the researchers from Google, we explored the following question. Do neural networks remember training data? As we all know, deep learning and neural networks have been really successful in helping pushing forward the frontier for AI and for many tasks. Deep learning and neural networks essentially are the state-of-the-art approaches in many different domains. But however, these neural networks also have very high capacities. And hence, one question is, do these neural networks remember training data? And if yes, can attackers actually exploit this to extract the secrets in the training data from just simply querying the learned models? So here is an example case study from our recent work. So in this case study, we train a language model from an email dataset called an unrun email dataset. A language model is simply a machine learning model where here, when given a sequence of characters or words, the language model can give a prediction for the next sequence or the next word. And in this case, with the unrun email dataset, it's already contained actual users' credit card and social security numbers in the original email dataset. And our work showed that with the trained language model using this training dataset, an attacker can devise by devising new attacks from just simply querying this trained language model. It can then automatically extract the original credit card numbers and social security numbers from the original training datasets. So this is an example demonstrating why it's important for us to be aware and pay attention to protecting users' privacy even when we are training machine learning models. So luckily, in this case, we have a solution. So our work shows that instead of training a vanilla language model, if we instead train a differentially private language model, then this trained differentially private language model still achieves very good utility. The efficacy does not get hurt much, but at the same time, it can significantly enhance the privacy protection for the data privacy. And in this case, our earlier proposed attacks actually are no longer effective. So what is differential privacy? So differential privacy is a formal notion of privacy. And intuitively speaking, so we say a function is differentially private if when we compute the function over two neighboring data sets, in this case, two neighboring data sets where one data set only has one data point more than other. For example, in this case, one data set has one more data point, Joe's data point, than the other data set. And then we call these two data sets neighboring data sets. And we see that the function is differentially private if when we compute the function over these two neighboring data sets, the computation results from computing these over these two neighboring data sets are very, very close. So essentially, in this case, the function itself is randomized, and the computation results is a probability distribution. And we see that the function is differentially private if the two probability distribution of the computed results from these two neighboring data sets are almost the same. So intuitively speaking, here a differentially private function provides a strong formal privacy guarantee for the user's privacy. Is that in this case, the attacker, from just looking at the computation results, will now be able to tell whether Joe's data point was used in the computation or not, and hence the computation result in this case protects users' privacy. For example, the attacker wouldn't even be able to tell whether Joe was included in the original computation or not. So differential privacy is a very powerful notion of privacy, but however, there has been very little work in deploying differential privacy in the real world. For example, previously only Google and Apple have used differential privacy in some very specialized applications. There are many challenges for enabling differential privacy for general data analytics and machine learning. So one, we need to provide better usability for non-experts. Most of the data analysts and data scientists don't even know about differential privacy, and there are many different types of differential privacy mechanisms, so they wouldn't know which one is best used for different types of analytics tasks and machine learning tasks. And also, we need to provide broad support for different types of data analytics and machine learning. And we also need to provide easy integration with existing data environments. So no existing systems address these issues. In our collaboration with Uber, we have developed new techniques and tools to address many of these challenges by building a framework for general privacy-preserving data analytics and machine learning. And with our framework, we can automatically write data analytics and machine learning pipelines to embed different types of privacy mechanisms into the data analytics and machine learning pipelines to automatically enforce the desired security and privacy requirements. And some of the technology that we have developed has been deployed at Uber to protect their internal data analytics. So putting together confidentiality-preserving smart contract execution and privacy-preserving data analytics and machine learning, this helps us to build privacy-preserving smart contracts to both protect the computation process from leaking sensitive information, as well as protecting the computation output from leaking sensitive information. So now let me briefly talk a little bit about the scalability aspects, how we built a new smart contract architecture, a blockchain platform architecture to enable scalable smart contract execution, in particular for complex smart contracts. So there has been a lot of proposals and discussions about scalabilities for blockchains. However, most of these proposals and discussions, they focus on only part of the scalability problem. And so most of these discussions and proposals, they focus on scalability for high transaction throughputs for simple payment transactions. So essentially high TPS, transaction per second, for simple payment transactions. But however, as the examples that we have seen, for many applications that people want to build on blockchain platforms, including in financial services, healthcare, IoT domains, and so on, oftentimes we need to deal with much more complex smart contracts. And hence, it's really important that we also enable scalability for these really much more complex smart contracts. And that's where the Oasis blockchain platform specifically focuses on. The Oasis blockchain platform is uniquely designed to enable scalability for complex smart contract execution. So first, let's look at why most of today's blockchain platforms do not scale. So a blockchain platform typically need to serve three main functions: consensus, how different entities reach agreement, and storage, storing transactions, contract state, and so on, and compute, to actually execute the smart contracts. And most of today's blockchain platforms bundle these three functions together, and each node needs to perform all these three functions. And hence, this is one of the main reasons that most of today's blockchain platforms have very low scalability, very low performance. So at Oasis, we take a different approach. We take a different approach and have a completely new architecture design for our blockchain platform that we call separating execution from consensus. Where and with this new architecture design, we enable scalability for complex smart contract execution. So with the Oasis blockchain platform, instead of having the consensus, storage, and compute, all three functions bundled together, as in most of today's blockchain platform, we decouple the three key functions, each one into its own independent layer. So we decouple them into separate consensus, storage, and compute layer, where in this case, each layer can scale independently, and also each layer can improve and evolve independently as well. And hence, the whole blockchain architecture also can evolve much more easily. By decoupling these three main functions into its own separate layer, and we enable separation of execution from consensus, and hence achieve a greater degree of parallelization and achieve greater scalability. And also at the same time, we utilize verifiable computing to tie these separate layers together to still enable the strong integrity and security for the overall blockchain platform. So we enable a strong layer 1 solution with both scalability and strong security and integrity guarantees. So with verifiable computing, essentially, in the so the consensus layer will order the transactions, and the compute layer performs the computation, executes the smart contracts, and the consensus layer will verify the correctness of the computation results. And in this way, by using verifiable computing, we can tie the different layers, the three layers together that I just mentioned, to achieve strong integrity and security. And we can utilize different types of approaches for doing verifiable computing, including majority votes and discrepancy detection, which I won't go into detail here. So to summarize, Oasis platform itself does not rely on secure hardware. So for example, the consensus layer of Oasis platform does not use secure hardware. And the integrity and scalability of the Oasis platform does not depend on secure hardware. And the scalability of the Oasis platform, as I mentioned, comes from separating execution from consensus, and the integrity comes from using verifiable computing. And in addition, the OSS platform provides a unified secure computing framework by combining secure hardware and other cryptographic-based techniques to provide privacy protection for the smart contract execution. And using this approach, we hope to provide developers with flexible choices to help them choose the best solutions for privacy protection for their applications, depending on their use cases and the desired security and privacy requirements. And also, we hope that the open source secure enclave design can help provide the community a shared foundation for secure computing in the future. So far I've given you an overview on the OSS blockchain platform architecture. So now let me give you a concrete example of an application that a developer is building on top of the OSS blockchain platform called Kara, a privacy-preserving tokenized data market for medical data. So as we all know, medical data is often locked in data silos. So the goal here is to incentivize doctors and patients to share data and improve medical research. So this is how the Kara application works. With the Kara application, the users or patients can upload their medical data to the OSS blockchain platform, and their data will be stored in an encrypted form. And a medical researcher can utilize the primitive provided by the OSS blockchain platform, the privacy-preserving smart contract primitive, to build his or her own smart contract. And inside the smart contract, it can contain code for training machine learning models. And the smart contract can specify terms of use. For example, it can specify how it can specify that the user's data will only be used for training a privacy-preserving machine learning model inside the smart contract. It will not be used for anything else. And also can specify how users will get compensated. If a user agrees to the terms of use in the smart contract, it can then contribute data to the smart contract. And as the smart contract collects enough data, it can then start training machine learning models, and then the medical researcher can then evaluate the effectiveness of the trained machine learning model. So as you can see, using this approach, it can significantly reduce the friction for medical researchers and pharmaceutical companies to gain access to data to help them develop machine learning models and help find better cures for diseases. So this is just one of many example use cases for a platform for privacy-preserving smart contracts at scale. And here, let me give you another example with a longer-term goal, how a technology like this can help solve some even more important problems. So as many nation-state leaders have recognized and stated, whoever controls and leads in AI will rule the world. So who is controlling or ruling AI and the world today? And so today we have big companies which are collecting a lot of users' data. And using this data, they are training personal profiles. And utilizing these personal profiles, they are providing personalized services to individual users. But however, the goal of these personalized services is to maximize company revenue. And also, we have seen examples where misuse AI is used for large-scale, automated, and targeted manipulation. So the question is, can we have a different future? Can we have a different future where we can develop intelligent agents and virtual assistants that are under user control? So these intelligent agents and virtual assistants can still utilize third-party services, but they will be providing personalized services to the users. And the difference here is that their goal is to maximize user value instead of corporate revenue. So using the technologies that I mentioned, on top of the Oasis blockchain platform, we can develop different types of these intelligent smart contracts. In addition to just training machine learning models in healthcare, we can develop intelligent smart contracts by leveraging different data sources for building better financial services models, for example, for credit score services, and for fraud detection, and for many other types of services and intelligent smart contracts. So the hope is that with technologies like this, we can help achieve the longer-term goal of democratization of AI. So at Oasis, we started this journey, and it was great to see the excitement and support from the community. And also, we recently launched our Startup Hub to help foster the ecosystem, where we provide early access to our technologies and technical guidance to selected startups, and also work together with our VC partners to provide guidance and insights to the selected startups in our Startup Hub. And also, we announced our Oasis Labs Fellowship to help support students to conduct research in wide-ranging areas for building privacy-first cloud computing on blockchain. And also, later this week, we'll be launching our Oasis DevNet with a number of unique capabilities and properties that were not available in any of the previous blockchain platforms. So we are very excited to provide these key features and capabilities to developers to help them build privacy-first applications. And these features include confidentiality framework to make it really easy and enable developers to build smart contracts that are confidentiality preserving, that will automatically protect the data and smart contract state for these confidential smart contracts. And also, we provide contract kits to make it easy for developers to develop different types of smart contracts. Our Oasis platform is fully backwards compatible with Ethereum Solidity smart contract language. And also, we enable Rust-based smart contract language as well. And we look forward to working with developers to build together on our platform, again, to build towards building a privacy-first cloud computing platform on blockchain to enable many new types of privacy-first applications that couldn't be built before. And one of the main reasons that I really enjoy working in the domain of blockchain is that it's so experimental. And the entire blockchain domain is conducting really exciting experiments, both from the technology perspective, as well as from even with the profound potential societal impact. And we hope that with the technologies that we're developing here, we can together work with developers to build these privacy-first applications to empower developers and users to together push forward the frontiers and to enable greater societal impact. And ultimately, data rights and privacy, these are fundamental human rights. So we are excited to have started the journey at Oasis Labs. And we look forward to working together with the community. And we welcome developers to come build their applications on top of our DevNet. And these are also information if you are interested in being involved in the open source Secure Enclave Keystone projects. And also, we are hiring. So for more information, you can visit Oasis Labs website and also follow us on Twitter at Oasis Labs. And thank you very much.